All right. So you ready for your head to explode?
Yep.
Good.
Always, sir.
All right. Okay. So this is one of those topics. It's really bizarre because in physics, the usually the most difficult thing are not really the concepts, it's the equations. Well, for some, not for all, because for some of you, you know, the equations are definitely not an issue at all. But for the average student, usually the equations are the issue when it comes to physics, not the concepts so much. That's not always the case, especially not here. So this section on special relativity, the equations are going to be really, really easy. They're not hard at all. You could have probably done them honestly, maybe way back in elementary school. That might be pushing it a little bit, but they are not difficult at all. What is going to be a little bit difficult uh, are the concepts. And that's because, our brain evolved to see things or think certain way, but there are certain things that, it's very difficult for our brain to visualize or grasp. Like, for example, we can easily think about three-dimensional objects, but when we start thinking about more than three dimensions, it's like, what? It's very, very difficult to visualize stuff like that. And special relativity would fall into that category, all right? So this is one of Einstein's babies, this theory. It's not the only one. He came up with a lot of very good theories. But this is the one we're going to focus on this is, I believe, chapter 10 in your book. And this has to do with you know, when an object starts to travel like at a pretty significant speed, certain weird things start to happen. Okay, so this is what we're going to discuss. Now, we are going to talk a little bit about one of his other theories called general relativity, because there is a tiny little bit of overlap between these two ideas. Remember, general relativity is an explanation of how gravity works. So I do want to actually sprinkle in some ideas with regards to general relativity. Um, but we're going to, again, focus mostly on special relativity. Okay, so here's just a little bit of background information. But before we start, can you see the screen?
Yep.
Okay, all right, very good. Okay, so some background. And this is actually, some of it, we talked about it last year in grade 11. So last year in grade 11, we learned about, Newton and his three laws. And, Newton's ideas actually, tied nicely together with another scientist, Italian scientist named Galileo Galilei. Do you remember he was the one who dropped objects out of a window and measured how quickly things fall to the ground? But he also did some work with relativity, and he talked about a scenario. Okay, and we actually talked about this last year too, and it has to do with an inertial reference frame. Do you remember what that means? An inertial reference frame?
It's not accelerating.
Yeah. So what are the two conditions then? So it's either not
Sorry.
moving.
Yeah. Or it's
All right.
moving with constant speed.
Yeah, very good. Or yeah, so when it's not accelerating, that means it's either not moving at constant speed. So here's an idea that he thought of. Okay, he said, what if we had someone in a ship? Okay, who obviously could not look outside the window. Okay, someone who's in a ship, not a spaceship. This would have been, I think, 17th century. So person in a ship, and he reasoned that that person that was in the ship would not be able to do any experiment to show that they were either uh, moving at a constant rate or not moving at all. In other words, not accelerating. Like, let's think about that for a second, okay? Like, imagine that you were stuck on the ship and you were trying to figure out if you were moving at a constant rate or you were not moving at all. what experiment could you do to show the difference between those two? Could you come up with one? I mean, I guess if you could look outside the window, you can kind of maybe deduce, whether you're moving or not. But let's say you couldn't do that. Would you be able to come up with an experiment? Anyone? The answer is you shouldn't be able to, because we talked about this yet last year. If you okay, imagine this, you drop a ball, right? Now, if you drop a ball and you're not moving, the ball just falls straight down. So let me just drop it, right? Just falls straight down. And if you're moving at a constant rate and you drop the ball, it does the exact same thing. Where it would differ, where you would notice the difference, is if you were accelerating. But then that would not be an inertial reference frame, right? So if you were accelerating, then that would obviously, you can tell the difference there, right? So I think I may have last year said something. For example, imagine you're in a car, you're moving at a constant rate, and you pour yourself a coffee, or you're standing still and you pour yourself a coffee. It would be the exact same experience. Where it would be different, obviously, if you're accelerating, then the coffee would just fly everywhere, right? That would be different. Now, this is an important concept. So you would not be able to tell the difference between these two, between moving constantly or not moving at all, okay? And what you're going to see with special relativity is, just based on a couple of key concepts, just some really weird things start to pop up when we really do, or we really start, diving into some of these big ideas, okay? Okay, so that's one. How many of you watched the video E equals MC squared?
Yeah, I watched it.
Yeah, I did.
So yeah, okay. So did you like it?
Yeah, it was cool. I liked Einstein's part.
Yeah, it's pretty interesting.
Yeah, I like the way. Do you recognize the narrator, John Lithgow?
Yeah.
Yeah, I think he was in. Was it Third Rock from the Sun or something like that? That's an old show. But anyways, so James Clerk Maxwell comes up in the video. Do you remember? He worked with Faraday. He was the brilliant mathematician. And he's the one, if you remember, Faraday was kind of ridiculed. Did he mention that in the video that Faraday's ideas were ridiculed?
Yeah, they said that.
Yeah, that was in the video, right? And then, you see the scene where he's really old and James says to him, I need to tell you something, right? Basically, he's like, that, we calculated that the electricity and magnetism can only happen at a specific speed, and it's at the speed of light. And in other words, Faraday was right. So he showed that, you think about light, electricity, and magnetism, that they're really the same thing. There's no difference. They're just different flavors of the same thing. Okay. So that's another big idea. And not only that, but there's a particular speed attached to this, right? Which is roughly 3 times 10 to the 8 meters per second. A second grade unification in physics. Very good. Okay. Now, if you remember last time, Michelson.
Sorry. Can I add something?
Definitely. Go ahead.
Because I really like Maxwell, and actually,
I've noticed that you bring him up often.
And the interesting thing, you can see how influential he was when you read actually Einstein's papers. Yeah. Especially the one in the electrodynamics of moving objects and those things. Yeah. He constantly repeats as Maxwell mentioned or as Maxwell found out. So he was very influential.
Yes, it actually, that comes up in the video, right? If you remember in the video when he's trying to seduce the girl. Yeah. He actually, I think he mentions let's have a drink and read Maxwell, or I think that's what he says to her. But
Yeah,
anyway,
he said something about it was so weird.
yeah. See, they didn't have. Gotta remember, girls, no Netflix back then.
Yes.
Yeah, obviously one of the greatest scientists for sure, or mathematicians, however you want to categorize him, mathematician, scientist, whatever.
Both.
I would class him. Yeah, I would class him as both. Okay, so then, if you recall, last time we talked about the Michelson-Morley experiment, which was, uh, thought of as a failure initially, but really led to great insight in that the speed of light is independent of the medium that's generating the light. Now, that's weird when you think about it, because last year, like we talked about relative velocity. So if I had, for example, imagine I had a car. I'm trying to drive a car, but why does that look like a car? So here's my car with the wheels, okay? And the car is traveling at let's say a speed of 100 meters per second, like this. And let's say, I don't know, maybe the car has a rocket on it and it shoots a rocket. And the rocket is traveling at 50 meters per second. Well, if you want to know the actual speed of the rocket, you would say it would be the sum of those two. The rocket would be traveling at 150 meters per second, okay? But let's say we did this. Instead of talking about a rocket, we talked about the car's headlights. Now, the headlights, if the car is stationary, we can measure the speed of light of the headlights as 3 times 10 to the 8. So imagine talking about the headlights of the car. So that speed would be c. Now, here's the thing. If I'm driving on a highway at 100 meters, by the way, 100 meters per second is like not realistic. Although, did you hear last week they caught some kid, 19-year-old, going at 308 kilometers per hour on a highway? Did you hear about that?
Where was that, sir? Here?
Oh
or-
my. Yeah, it was here. I think it was on a 401, I believe. 308
Uh,
kilometers per hour. Okay, that's a little bit slower than 100 meters per second, but that's still pretty fast. Okay, now if I'm stationary, I shine my headlights, I can measure the speed of light as c. Here's the difference though. If I'm driving down the highway at 100 meters per second, so I'm actually faster than that crazy kid at 308 kilometers per hour, and I measure the speed of light, it's still c. It's not c plus the 100 meters per second. That is very different. That is very different than what we talked about last year. So the speed of light is the same. That's not, again, it's kind of hard sometimes to wrap your head around that because that's not what you're used to, right? You're used to relative motion. Here, it's different. Speed of light is constant. Okay, I want to pause that thought for a second because I want to actually talk about Einstein's other great idea. Well, he had a few, I said, right? So the other one was general relativity, or GR. We'll call it GR. Call it special relativity, SR. Okay, so this is just to highlight something, okay? The reason why I'm mentioning this is because there's a little bit tie-in with what I want to talk about. All right, so here's an idea that he came up with. And again, I don't know how he came up with these ideas. I mean, it's kind of like, sometimes you wonder, like, they're same human, like same species of human or something. But here's what he thought of. And I was like, this is unbelievable. He reasoned the following. He said that gravity, remember, acceleration is a non-inertial reference frame, right? So gravity would be example of a non-inertial reference frame. So it's not moving constantly, or it's not stationary, right? Gravity, there you experience a force, a net force. Okay, he said that gravity and the following, which I'm going to describe to you, were the same thing. So imagine this. Imagine that you were in a box. Okay, you're in a box. And again, it's kind of like the ship. You can't see outside. So you're in this box. Now, you're standing in the box. You know you can feel the direction of gravity. You know that it would be pointing down. Okay, that's fine. Now, what if I did this? I put you in a box, outer space, and there's a rope attached to the box. Now, if I pull, imagine there's some mystical being that could pull on that rope with a force going up, okay? What would you experience? So imagine you're in outer space, okay? You're floating around in this box. All of a sudden, the rope gets pulled. Let's say on my sheet, it's getting pulled up, okay? What would you experience? Anyone want to guess? Which way would you move? Anybody? Would you move up? Or would you move down? So you're in this box, right? You're floating around. The box is attached to a rope, and some magical being, we'll call him Thor or Captain America for you, Emma, pulls the rope. Let's say pulls the rope. No problem. Pulls the rope up. What would you feel? Which way would you feel the force?
Downwards?
You would. Why? Because as the elevator is coming, or this box is coming up, you're going to be pressed
Down.
towards the floor.
Yeah.
Right? You're going to be pressed towards the floor. It's like when an elevator ascends, you feel heavier, right? It's the same concept. Now, this is what he reasoned. He reasoned that you could not tell the difference. If you're in this box, you could not tell the difference between whether or not you're experiencing that downwards force because of gravity or because there's some upwards acceleration that's pinning you to the ground. Now think about that for a second, okay? That's like really out there, but it kind of makes sense, right? When you think about it, that makes actually a lot of sense. So they would feel the same to you. Okay. So the reason why I wanted to bring this up is for the following question, okay? So let's say we did this. Let's say you had a flashlight, okay? So you say you had a flashlight, and let's make the flashlight yellow. Now, let's say you shine the flashlight perpendicular to the direction of the force, okay? So let's say you're shining a flashlight like this. All right, now here's my question. Would the beam of light, imagine you can measure the beam of light like with incredible accuracy, okay? Would it be straight or would it bend? Would it curve or would it travel in a straight line? What do you think? Who wants to guess? Now, listen, how old are you guys now? 12, 13? What's your average age?
Yeah, we're all
10. No, 10. I'm 10 years old.
All right,
Yeah.
anyone ever use a flashlight?
Nope.
Seriously?
No, I have. Some.
Okay. You've used a flashlight before? Okay.
Yeah.
Does the flashlight travel in straight lines? You probably never thought of that, right? Okay, put it this way. If you shine the flashlight at something, you're going to point to the object you want to shine the light on, right? Do you notice the light beam bending downwards because of gravity?
No.
No. Okay. So gravity would not, well, you wouldn't notice that though. So then what would this observer see?
A straight line?
They would see they would see a straight line. So here's the thing. Well, why can't they see the curved line? Because let's say I do this. Let's say I have the box, okay? And let's say this dot represents the pulse of light, okay? Now pulse of light over time is going to move, let's say, to the left, right? So maybe at one moment in time it's there. Now, if we're talking about the object being pulled with a force. Okay, something in the chat. Hold on, let's take a look. Okay, let's address that. Okay, Maya, hold on. Let's address that because this is actually going to go back to this. All right. So here's the idea. Let's say that we have the upwards force, right? Now, what's going to happen is as that pulse of light travels to the left, then what's going to happen is if we see it bending like this, because the elevator is going to move up, right? So as the elevator moves up, the light will bend like this because the elevator is moving up, right? But the problem is that can't happen. The reason why that can't happen is because of what I just circled. That this is something called the equivalence principle. All right? It reminds me exactly of what Galileo said for the person on this ship. What he said was there's no experiment that you could do to distinguish between not moving or moving at a constant rate. Okay. If this is true that gravity and being pulled up with a force are the same, then there should be no experiment that you could do to distinguish between the two. So if the light curves, then that means you could tell. You'd be able to tell. You'd be able to know that the elevator is being pulled up by some mystical being. But you can't do that because then that would violate the equivalence principle. The reason why I wanted to bring this up is because you can see there's a connection there with what Galileo thought about. But there's actually something else too I want to address with this a little bit later on, okay? Because here's the thing. The person outside the box would see the curved line. So let's say there's an observer that is not in the box and was watching, I imagine they could see in the box, right? Was watching the path of the light, they would see a curve, which actually would explain why light curves in a gravitational field. This would be like the thought experiment that illustrates that. But it also illustrates something else, which I'm going to talk about later. Okay? Any questions about that?
Can you repeat what the equivalence principle is again?
So it's the same as the principle of relativity. The difference is in the principle of relativity, we're talking about an inertial reference frame. And for the equivalence principle, which if you had a good teacher, would have actually written down equivalence principle on the sheet. So the equivalence principle is kind of like, it's in the same spirit as the principle of relativity, in that you can't do any experiment to distinguish between, so you're in a box, there's no experiment that you could do to distinguish between the effects that you feel from gravity versus that magical force being pulled up on that rope. They would feel the same to you. Right?
Yeah.
So if you saw the light, like, because you know when you shine a flashlight on the wall, it does not bend. It goes in a straight line. But imagine that you were accelerating. Well, then, you know, if it curved, then you'd be able to tell. And then you shouldn't be able to tell. So that person would not see the light bend. Otherwise, they would be able to tell the difference between the two. I know it's not easy to wrap your head around these ideas. I'll be honest with you, it's not. Like I said, the math, when we get to the math of this, math is easy. It's the concepts that are a bit tricky, a lot tricky actually. Okay, so back to SR, special relativity. So here's the idea. The idea is, and this actually combines two simple concepts. And the two simple concepts are this. One is principle of relativity, right? That the laws of physics are the same for all inertial frames of reference. Okay. That's what we talked about before, being on the ship, right? You couldn't tell the difference between moving at a constant rate or not moving at all. The other one is this, principle of invariant light speed. The light is always propagated at the same speed. And by the way, that would actually then tie back into this, because if the light did bend like this, then its speed would actually be greater than c. Because you would have its speed going this way and a speed going that way, and you would have a speed greater than c, which you can't have. It's another interesting idea. So these two concepts, they're going to lead to some pretty amazing ideas. They're really amazing ideas. So let's go back to, because we talked about, I mentioned this one last week. I didn't want to go into it, okay? So here is a thought experiment, all right? Here's the idea. Imagine, and by the way, if you look up this answer, you're going to get like a wide range of answers. Most consistent answer will be, you can't do this. It's just not possible to do this. Like travel at the speed of light, all right? But let's imagine that you could. You could travel at the speed of light. And you hold up a mirror. So imagine this. You're sitting in a subway or train, and the train is traveling at the speed of light. So I'm sitting, and I hold up a mirror, okay? And let's say we're moving this way. All right, now, Einstein thought about this question. He's like, what would happen if I was traveling at the speed of light and I held up a mirror? Would I see myself in the mirror? Now, I want you to think of this. Think of Galileo on the ship, right? What he said was, there's no experiment that you could do to distinguish between you moving at a constant rate or you not moving at all, which is one of the main ideas of SR. It's right there, principle of relativity. Okay, so does he see himself? What do you think?
No.
No?
He won't see a reflection.
So the answer that I came across from, do you know who Veritasium is?
Yeah.
Yeah. Yeah. He's got really good stuff on YouTube. He says that he will see himself. And the reason why he will see himself is because if he didn't see himself, then it would violate the principle of relativity. Then he would be able to tell that he is moving at a constant speed, which obviously in this case would be the speed of light, right?
But
so it would violate.
Isn't it an inertial frame of reference? So we are saying that it's we are having an inertial frame of reference, right? So it's not accelerating. So
not accelerating.
Basically, yeah. So basically, you are moving with the speed of light. So you know it already.
No. No, but okay. So yes, I did say he's traveling, but let's say he didn't know that. Okay, he didn't know he was traveling at the speed of light. And the question is, would he be able to tell that he is moving at the speed of light or not, right? And if he couldn't see himself, then that would violate the principle of relativity. Then that would be an experiment that he could do to distinguish between the two. Now, I'll tell you why this is not a reason why. Because there's a bunch of things that happen when you travel at the speed of light, which we'll talk about a little bit later on. And one of the things that happens, everything comes to one point. All lengths are contracted to basically zero. It's weird, but also things like time changes and masses change. So the real answer, if you look this up, is you just can't do this. You cannot travel at the speed of light. So this is like an unreasonable question to even ask in the first place. But what we're going to do is we're going to come back to this question, and we're going to modify it slightly and ask, what if he was traveling at near the speed of light? That's something we can do. I can't, but there are certain things that can't travel at near the speed of light.
I didn't understand why he sees himself. Because isn't the light moving at the same speed as he's moving?
Yes.
So it would never reach the mirror, right?
Yeah, but then he'd be able to tell. I know, it's one of those questions. It's like, yeah, because I'll be honest with you, when I first saw him, like, yeah, he can't see himself. But then if you watch the Veritasium video, he's like, well, then he would be able to tell. So it's like, what's going on here? It just, I don't know. It's one of, like I said, the math is going to be easy. Conceptually, this is going to be a very, very tricky. Okay, so here's what we'll do. We'll talk about the first thing that happens when you start traveling really, really quickly, okay? And then I think when we come back together next time on Thursday, we'll talk about the other effects, because there's a bunch of effects that happen. Now, again, this occurs when you start traveling fast, and the question is, what does it mean by fast? Like, you have to be going, I would imagine, at least more than 10% the speed of light. So that would be 30,000 meters per second. So you're never going to experience this in your regular life, but there are things that do experience this that we can actually talk about. One of the things that happens when things start traveling really fast is time changes. Okay. Time changes. Now, let's talk about this. This is a really, really interesting one. So this is how Einstein thought of it. He said, let's visualize a light clock. All right, a light clock. So a mechanism that keeps time by basically imagine a pulse of light that goes from here down and back. Okay, there would be like one cycle, right? So imagine a light clock that this is how it kept time, by bouncing a photon of light down and then back up. Now, if you were, let's imagine you're on a train. So you're on this train. Okay, so here's my train. Okay, and I'm here, and I watch a light clock. Now, what do I see? If the train is moving or it's stationary, to me, it would look the same, because remember, I can't violate the principle of relativity. There's nothing that I could do to distinguish the two. So for me, it would look like the light clock, the photon of light would simply go up and down, down and up like this, right? It would look no different. Whether I'm moving at a constant rate or I'm stationary, the beam of light would simply just go down and then up, down and up. Okay. But what if I am watching somebody else moving? So imagine someone else is on a train. The train is moving, and they have a light clock. And the light clock, the photon is bouncing, back and forth. Now, what would I see? Well, I would see something very different. I would see the photon of light travel on diagonal lines. So let's say it starts here. It would look, imagine my train is moving like this, okay? So it would look like this. It would go this way, and it would go this way, because it's a combination of the photon going up and down like this, but also the train moving like that. So it would produce motion on angles. So that's what I would say. I would see something very, very different. Now, here's the interesting bit. Let's imagine that I'm measuring time on the train. Okay. Now, imagine that, one cycle would be from here back to here. Okay, that's a cycle. Now, what I would notice is that for me, my clock is just going up and down like normal. But the person who's observing the moving clock would see it tick at a different rate. Why would it tick at a different rate? They would see something different. All right, so let's look at this, okay? Because again, this is one of those things where mathematically it's not so bad. It's just conceptually it's a little bit challenging. Okay, so let's look at this. Imagine my moving clock just going up and down. I'm going to explain like what this is, okay? So imagine my moving clock just going up and down when it's stationary, like this, okay? Here's what I could say. I could say that the distance that the photon travels would be a function of the speed of light times the time. I'm going to call it the stationary time, okay? This is the clock that's, from my perspective, not moving. Okay. Now, I want to compare it to what the person who's like observing the moving clock would see, because they would see something different. They would see the clock's path as diagonal lines. Okay, so here is where we're going to have to look at some of these values. All right, so here's the thing. Let's say that this represents v is the speed of the train. Okay, so my train is moving, let's say to the right. Okay, now here's the thing. Normally we'd think, well, okay, well, this is c, the speed of light going, going up and down. There's my photon of light. So we would think, okay, well, this has to be c. Therefore, these diagonal lines would represent this, right? The sum of that. But what would be the problem with that? Anyone want to guess?
You can't add to the speed of light?
Yeah, it would violate this, the principle of invariant light speed. In other words, that would suggest that the speed of light would be greater than c. Okay, so what would it be then? Well, actually, what it turns out to be something like this. What we could say is that, let me just fix the color here. We could say that this would be c, this would be v, and this would actually be c squared minus v squared. So this would be your speed of light. This would be the speed of the medium. This now becomes the speed of the photon going up and down, which is less than the speed of light. Okay, now, why am I showing you this? Because now we're going to look at something. We said that the distance that the light travels is a function of c times the stationary time. But now let's look at the moving clock. All right, so we can say the moving clock would be the distance over the speed. Okay, same idea. But the speed of the moving clock, if we just look at it going up and down, would be defined as c squared minus v squared. Okay? And the distance, we can say the distance is simply c times the stationary time. Okay. Now, here's how we can because I'm trying to show you how what this is. Okay, what is that? And if you don't understand this, it's okay, because you don't really need to know the derivation. But I came across it, like, you know what, maybe we should take a look at it. It seemed kind of interesting. So let me show you how this derivation, which is actually this, where it comes from. Okay. Otherwise, it's just sitting on my screen. It's like, where did that come from? So the numerator is the c times stationary time. Now, what we can do is we could factor out the c squared like this. So we can remove that. Now, what's the square root of c squared? Well, that's just c. So this would cancel out with that. And now what you have is an expression that looks like this one. So this is how it's derived. This 1 over this 1 minus v squared over c squared is something called the gamma factor, which I'm going to try to draw the symbol. Kind of looks something like that. Okay, so another way of writing this equation over here is we could say that the moving time is the stationary time times the gamma factor, which kind of looks like, let me fix that a little bit better. Okay. If you didn't understand that, it's okay. What you have to know is this, that the two observers are not going to experience the same passage of time. Now, that's very, very bizarre. The person on the train is going to experience a certain passage of time. The person that is observing the person on the train is going to measure a different passage of time. Now, what will they notice? Well, okay, if observing the moving clock is a function of the stationary time over square root of 1 minus v squared over c squared, what's going to happen is, as we approach a higher speed, the moving clock will start to tick at a slower rate. Let me show you what I mean by that with one example, okay? So imagine this. Imagine a person is on a rocket ship and flies by at 0.8 c, okay? 0.8 speed of light, so 80% speed of light. And this person on the rocket ship reports that according to their clock, it took 10 minutes, all right? What would the stationary observer report, however? So the person watching the rocket ship, watching the moving clock, what would they say the time was for the trip? Okay, so what we're going to do is we're going to calculate the time that that person would observe the moving clock to actually have elapsed, okay? So we said it's TS over 1 minus v squared over c squared. Okay. So the stationary time, would be the person who's on the rocket ship, right? That's their stationary time. For them, they're traveling at a constant speed. To them, their clock looks like the stationary clock, the one that's just going up and down. Okay, it's just going up and down like a normal clock would when it's stationary, because we said, principle of relativity, that if they're moving at a constant rate or they're not moving at all, it would look the same to them. So their stationary time would be 10 minutes. Now, the person who's observing the moving rocket would have measured a different time. So it's 1 minus v. Now, you don't need to convert this to the actual speed of light. You can just do 0.8 over 1. 0.8 c over c squared. So you can just do 0.8 over 1. So if we do that, we get 10 over the square root of 1 minus 0.64. So it's going to be 10 over the square root of 0.36. So that's 10 over 0.6. So what is that, like about 15 minutes? Approximately? It's close to that. It's a little bit more than that. It was 16 minutes, I think. What is it exactly? 10 divided by 0.6. 16.7. I was way off. So 16.7 minutes. Okay. Let me just fix this. I'm just going to round it off to 17, okay? So 17 minutes. Okay. So you could see that the person on the rocket ship thinks 10 minutes have passed by. The person who's outside the rocket ship measures 17 minutes passing by. That's bizarre, right? You think about it, what do you mean? How can they both have different time measurements? Now, that's something that you would think, okay, well, maybe Einstein was, maybe drinking a little bit too much, maybe smoking a little too much, and maybe he came up with some crazy ideas, but they're all voodoo. Turns out this is true. They've done experiments to show that when things are moving at fast rates, their time slows down. Now, what does that mean, their time slows down? Okay, you can think of it this way. The person outside the rocket ship has experienced 17 minutes of elapsed time. The person on the rocket ship or in the rocket ship experiences less time having passed by, 10 minutes. Now, what that actually means is, biologically speaking, they would have aged less. Think about that for a second. They would have aged less. So I want to end with an idea. This is a very famous paradox. But anyway, any questions about the math of that? Like, see how not very difficult? I guess the tricky part would be maybe you might screw up where to put the 10. But remember, the person who's observing the moving clock always experiences more elapsed time. Okay, more elapsed time they would experience than the person doing the moving or the thing doing the moving. Okay, so just if you remember that, you should be okay. So I want to end with this, okay? And then on Thursday we'll just pick up from where we left off. It's called the twin paradox. I don't know who came up with it. I don't know if Einstein came up with it. I don't think he did. I'm not sure. Maybe he did. And here's the idea, okay? Now, on the surface, you might think, well, I know the answer to this question right away. So we just said that if you're in a rocket ship, we just showed it. If you're in a rocket ship and you're traveling at a pretty significant speed, and by the way, we can't even get close to that speed, so you don't have to worry about this. You would experience less time having elapsed. So if you're on Earth and your brother or your twin brother or twin sister takes off on a rocket, you would think the automatic answer is, well, okay, they're going to age less. The person on the rocket will experience less elapsed time. So when they come back to Earth, you would think they would have aged less. You would be older, they'd be younger. Okay. But the reason why it's called a paradox is because, all right, here's where it gets a little bit weird. Okay, so if the person on Earth is measuring the moving clock on the rocket ship, it would show that it's ticking at a slower rate. Okay, so we established in the previous question. But this is relative motion. So what if the rocket ship is looking at the clock on Earth? To the person in the rocket ship, the clock on Earth is the moving clock. You see the problem there? So the person on Earth looks at the rocket ship and looks at the clock, now assuming they can see the clock on the rocket ship, and that's the moving clock. But then, you know, person on the rocket ship would look at Earth and see that as the moving clock. So that's why it's called a paradox. But then who's going to be the older twin? Person on Earth, person on the rocket ship. Anyone want to guess? So the problem with this question, the reason why it sounds like, oh, is this totally like ruining what we just talked about? Like what's going on here? Is this. The problem with that question is, well, it kind of violates the first one. Because for the rocket ship to leave Earth and then come back to Earth, it cannot always be at constant speed. It has to accelerate, right? The rocket has to slow down, stop, and then speed up. So, you know, it's never going to be it's not always in an inertial reference frame because there is acceleration going on. So then, you know, the answer, if you look this up, the answer to this question is, well, it's the person on the rocket ship would actually experience less time. So I guess what I'm saying to you is if you don't want to age, throw yourself on a rocket ship, go really, really fast. You could see basically at 80% the speed of light, you're not quite going to age at half the rate. Not quite at half the rate. But what's really interesting, though, I'm going to end with this, is, and this is, I guess, you know, the problem with the first question with Einstein looking in the mirror. What does this predict if you're traveling at the speed of light? Anyone want to guess? This makes a bold prediction about traveling, time and traveling at the speed of light. Who wants to
I think because the denominator is going to become 0.
Yeah.
So we'll have like something over 0, which is kind of infinitely undefined.
Yeah, so it actually makes the prediction that time comes to a stop. That's the prediction, that time comes to a stop. All right. I think this is fun. I like it. I think it's interesting. Let me stop recording and I'll take